Calculus is the branch of mathematics that studies continuous change. It's an expressive and powerful tool that helps us describe many processes in our universe that involve changing variables. Today we'll be looking at the core ideas that serve as the foundation of calculus. Welcome to Infinite Insights. To illustrate how calculus can help us solve such problems, consider this simple scenario. A mass is dropped from a height and falls freely in a vacuum. According to kinematics, we can model the distance traveled by the mass at any given moment in time using this formula, s equals half gt squared, where g is the acceleration due to gravity, 9.81 meters per second squared. Using this formula, we can say, for example, that after 10 seconds, the mass would have traveled half times 9.81 times 10 squared, or 490.5 meters. Therefore, we can calculate its average speed over this duration as distance divided by time. 490.5 divided by 10 equals 49 meters per second. However, it is clear that the mass is not traveling at this speed throughout the 10 seconds. It starts at rest at the top and speeds up over time. What if we wanted to know exactly how fast the mass was going right at the 10-second mark? Well, using the same average speed formula will not work this time, because at the instant of 10 seconds, the mass hasn't traveled any distance and the time interval is 0, so we cannot get a reasonable answer this way. We need to avoid dividing by 0. We need a different approach. Let's try to visualize this problem by plotting our function as a graph. Earlier, when we calculated the average speed of the mass, we took the distance moved and divided it by the difference in time. This is equivalent to finding the gradient of the line between the points on the graph where t equals 0 seconds and t equals 10 seconds. We need to avoid dividing by 0 outright, but we need a way to get as close as we can to finding the gradient at 10 seconds. What if we just moved the first point closer and closer to the second point, until eventually the time interval is so small it doesn't matter? Let's define a new variable delta t that will represent this time interval. The goal is to find some way to make this number reach really close to 0, but without causing division by 0 problems. We place the first point at t equals 10 and the second point at t equals 10 plus delta t. Now we evaluate the function at both these points and plug them into our gradient formula, which is essentially the same as our average speed formula from earlier. Simplifying, we get this expression for the velocity at t equals 10 seconds. Now we can safely substitute t equals 0 into this expression and get the velocity at t equals 10 seconds to be 98.1 meters per second. How do we get a real answer this time? What we've done here is we've applied the formula for average speed for a small region near t equals 10 seconds and tried to find what happens when the time interval got closer and closer to 0. In calculus, approaching a value this way is called taking the limit. So we can say that the limit of the average speed as delta t approaches 0 is 98.1. This same concept can apply to nearly any other function that we might want to analyze, and it's the core idea of differential calculus. This is how we can define the rate of change of the value of a function f with respect to its input x. Today, we've looked at some fundamental concepts that serve to introduce the main ideas of calculus, and we got an intuitive understanding of limits, which can help us when we can't evaluate functions directly. If you think you learned something new today, feel free to share your thoughts in the comments below. Thank you for watching, and I'll see you in the next lesson.